Well, so I believe this my slides are also visible to all of you, right? Just a quick response.
Yes, sir.
Thank you. So in last class, we understood the concept of Fermi distribution or Fermi statistics, and then we also understood the concept of uh, density of states and how this density of states and this Fermi-Dirac distribution help us to count or quantify the number of electrons as well as number of holes in semiconductor, as well as we have understood these two concepts. Primarily will we need to deal in case of semiconductor, that is either equilibrium or steady state. So so this is again mm, the same definition of density of states. So this is the number of states available to be occupied by electrons per unit volume and per unit energy. So when defining this number of states or this density of state, so remember, sometime we miss this per unit energy because it is density. So this density is there, so it means something per unit volume. So, but we should also remember that this is per unit energy also. So now, what is this graph all about? So see, there are different type of semiconductor considering its dimension. So that means typically whatever the semiconductor device we see, so this is three-dimensional. That means if we take any semiconductor device, it has X, or Y as well as Z. Now, you know, in just recent time, there are few semiconductors or the semiconductors, a few semiconductors emerging, which has sometime two dimension like that. Okay, let me XYZ. So this two-dimensional semiconductor has only X and Y. So that means a semiconductor, let's say this the plane of this a sheet of paper, and now this sheet of paper, if it is made of let's say semiconductor, so then this is a two-dimensional semiconductor, and in that case, its density of state will change or will be different. So this graph, if you see, this is the density of states variation with the energy E. So again, this density of state is a function of energy E. So how this density of states or the number of available states for your electrons to be occupied as well as for your holes to be counted, I would say. So that will change with the energy. And this dependence will be different. That means this density of state dependence on energy is different considering the dimension of semiconductor. Now, the majority of the discussion in this E311 will discuss only this 3D semiconductor. That means the semiconductor device, whatever we'll discuss, it has both X, Y, and Z. But the a few emerging semiconductors there are, so like 2D material, if you know, like the 2D material, now this there are many applications. So it is like MOS2, this is molybdenum disulfide or tungsten disulfide. There are a lot of this transition metal disulfide material, so which has this two dimension. So this Z direction is absent in this type of 2D semiconductor. So only the electrons and all the calculation we need to perform considering that the semiconductor has only X and Y, these two dimension. And when we have this two dimension of our semiconductor, the density of state variation with the energy will be different. It will not be the same. Again, similarly, we can also have some semiconductor, like if you know that nanowire. Nanowire means, so there is one particular like the semiconductor is a single dimension. So there is no Y as well. So only you have a semiconductor in x direction. So this is a very thin nanowire. It is like a, you can say like a one single piece of hair. Again, this hair is also having a larger diameter than this nanowire. So this is essentially this semiconductor has only one dimension. All the electronic movement and other things are confined to one dimension only. So in that case, the density of states is different. So again, finally, we also have semiconductors which has no dimension. So that is called quantum dot. So it has neither x nor your y as well as nor z. So quantum dots, if you know this, you must have heard of or must have seen the advertisement by Samsung. There is a QLED, quantum dot LED TV. So those are like they are the pixel, each the pixel which are glowing and eventually giving you the whole like this picture. So they are made of a single quantum dot. So that is a semiconductor, but it has no dimension. So in that case, if you can see the density of state completely different than compared to others. So this is the density of state variation with the energy E depending on the dimension of semiconductor. Okay. So since our majority of the discussion in this particular course will be confined to this three-dimensional semiconductor, so we'll discuss mainly this variation of density of state with the energy E. So, but so again, why we need to know? Just I'm giving you this brief background, because if you in future, if you take any advanced course or if you try to understand the different semiconductor, so the counting, because see, density of state is essential parameter to calculate the total number of carriers. So now from this distribution, you can easily guess that the number of carriers will be different depending on the dimension of semiconductor. That means whether you have 3D semiconductor or bulk semiconductor or 2D or 1D or zero dimensional semiconductor, the carrier concentration will be different because of this density of state variation. So now this is again something which we have already discussed. This is how we are calculating this density of states. It is the number of states in this energy del E, and then divided by del E and volume. So because overall this is number of states per unit energy per unit volume. So this is a just calculation of your density of state in case of density of states in the conduction band as well as the valence band. And you need to look at the unit. So it is the number of states per electron volt per centimeter cube. So once again, this is the Fermi-Dirac statistics, which we have already seen in the last class. So this is the probability that an available energy state at E will be occupied by an electron at absolute temperature T. And you can also see, like in last class, we discussed how why this. I think it has this equation. I think we have that formula. No. So this is F equals to 1 upon 1 plus exponential E minus EF divided by KT. And this particular graph represents this equation. So here this is a 0 Kelvin, and then when we'll increase the temperature, just the take home message from this particular figure. See, when you will increase the temperature T2 greater than T1. So now see this, how this extension of your Fermi-Dirac distribution is increasing with energy E. And at the same time, so that means see here, this is increasing with the temperature. And at the same time, this is decreasing, like how the distribution of Fermi-Dirac statistics is varying with temperature T. So more will be the temperature, it will be it will go down and down in this when your energy less than EF. But when your energy E greater than EF or above Fermi level, so in that case you will have this kind of distribution. Why we are discussing this, we'll soon discuss in the coming slide, like why we need to understand this particular behavior of Fermi-Dirac statistics with the temperature. So this is something once again we discussed in the previous discussion. So this is a Boltzmann approximation, but when this E minus EF greater than 3 kT, so then we can have this Boltzmann approximation from our this Fermi-Dirac distribution, because again this Boltzmann like in most of the problem or discussion will use the Boltzmann approximation. So the important this statement from this particular slide is there is only one Fermi level in a system at equilibrium. So I don't know whether I have mentioned this in the last class or not. That is why we discussed these two conditions, equilibrium and steady state. So equilibrium, once again, if I try to recall what is the equilibrium, just if we try to see recall that example, any semiconductor at certain temperature under dark without any electric field, without any magnetic field, uh, under dark essentially means without any optical field. So then it is called the semiconductor under equilibrium. So there will be no external energy perturbation or external energy disturbance apart from the temperature. So that is called equilibrium. Now, if your semiconductor is under equilibrium, there will be only one Fermi level. So remember this statement. So because again in your PN junction discussion we'll see in when we'll bias our PN junction diode, that means it is not in under equilibrium condition, or whenever we'll bias our diode at fixed voltage and we'll get constant current, so that we can consider as steady state condition. So there we'll see that Fermi level may get splitted, and then there is some concept called quasi-Fermi level. So that we will discuss. So in that case, because in that when your like PN junction diode is under steady state or is under non-equilibrium condition, there we may have two or multiple Fermi level. But if our semiconductor is at equilibrium, then there will be only one Fermi level within the system, like throughout the system. There will be no difference in the Fermi level if it is under equilibrium. That means if the semiconductor is only at some certain temperature without any external energy. So now this is a pictorial representation how we can calculate this carrier concentration in from density of state as well as the Fermi-Dirac distribution. So now see the so this is the density of state variation, because here we are considering three-dimensional semiconductor. So we have already seen this kind of parabolic variation of density of state with the energy E. So this is the density of state variation with energy E in above or at the in the conduction band, and this is the density of state variation with energy E in the valence band. Again, this is in case of hole, because again hole and electron is always like taking the opposite behavior or opposite see now the curvature is just opposite. So now this is the density of state variation we know. Now next our parameter which will decide this carrier concentration is the Fermi-Dirac distribution. Now see this Fermi-Dirac distribution, here we are considering this is a n-type semiconductor. So that and that is why you can see here. So there are more number of electrons in the conduction band compared to the holes in the valence band. So we have more number of electrons in here and then the holes. So that is why our Fermi level now is closer to conduction band. And this Fermi level has this kind of distribution, and this is obviously T greater than 0 Kelvin, because we know that at T equals to 0 Kelvin we have exactly square a type of distribution of our Fermi function. So, and since this is at your in-type semiconductor. Once again, if we try to recall in our from our previous discussion that there is some concept called intrinsic Fermi level or EI. So again, this that the energy difference between EI and EF will quantify or will decide how many electrons or how many electrons as a magnetic area you have in a particular n-type semiconductor. So higher will be the energy difference between EF and EI. That means the closer your EF will be towards your conduction band bottom, so then your overall semiconductor will be more and more n-type. That means the electrons will be more and more. And from this distribution, you can easily once again understand. See here. Here you have this. This is the this is the density of states available. So in case of your this bulk semiconductor or 3D semiconductor. Now see, there is a significant amount of Fermi-Dirac distribution penetration above the conduction band. So now this portion, so this is this extension along with this distribution. If we multiply, or if you just multiply and integrate, so then you will get this kind of electron concentration finally. So few more comment or observation from this graph. See, when this is a more n-type, so that means your Fermi level is closer to your conduction band. Obviously, the penetration of your Fermi-Dirac distribution above the conduction band will be higher than the the absence of your Fermi function, I would say. So because this is a 1 minus Fe. So because this is a 1, and this is the 1 minus Fe. Because again, this it helps us to quantify the holes 1 minus Fe. So from this distribution, we can understand that higher will be this n-type behavior, lower will be the p-type. Like simply like that we know that in case of if we dope it n-type, so obviously we'll get more electrons compared to holes. And the same concept we can also understand using this Fermi-Dirac distribution. So similarly, you can see that electrons are majority than the holes. Another observation just I am mentioning here, see the maximum number of electrons will be here, not exactly at the bottom of the conduction band, but at little above the your bottom of the conduction band. Again, for this particular course, perhaps we don't need this, but this you can remember, because in optoelectronic device, where you need to have this transition from the transition of electrons from the valence band to conduction band. So there, sometime we need to discuss all these things. Again, remember the difference between this energy level and this energy level at room temperature is very small. Like electrons can easily go from here to here just due to the thermal energy. But at 0 Kelvin, you will be able to find all this effect. So the effect is here our electrons are more little above the conduction band. It is not that at the bottom of the conduction band we have more electron. A little above the conduction band we have more electron, and the reason for this, if you can, if you just look at this graph or this behavior, this density of state behavior, you can easily see, because density of state is 0 at this bottom of the conduction band, and it is gradually increasing. So that is why this higher number of electron population will be little above the bottom of the conduction band. So these are some observation from this particular figure. And okay, so now let us try to quantify. So this is once again the quantification. We have done this quantification in the last class, but differently. Just we considered that proportionality constant, and then we did that calculation. So this is some in detail calculation of your carrier concentration. That means electrons as well as holes, and these are the effective density of states, and how it is defining your total carrier concentration. And these are something which we have discussed, and this is something just we have discussed. So how this your 1 minus Fe is deciding the so this is, again, you can see this is an intrinsic semiconductor. So in case of intrinsic semiconductor, the penetration of Fermi-Dirac distribution in above the conduction band and below this valence band is almost same, because your this EF is equals to EI. This is intrinsic semiconductor. But in case of N type, you can see this your Fermi-Dirac function shifted up, or that means closer to your conduction band. And in case of P type, your this Fermi-Dirac distribution moved down in energy diagram. That means it is closer to your valence band, and that means you will have more 1 minus Fe than your Fe inside the conduction band. So that is why you will get more number of holes in case of P type. So this is, again, this is that enlarged portion of this region where your Fermi-Dirac distribution is going inside the valence band. So this is that same concept, but for the all material. That means intrinsic, N type as well as P type material. The only difference you can see, once again, this the difference is the Fermi level position. So Fermi level in case of intrinsic at the middle, but in case of N type it is closer to conduction band. In case of valence band, in case of P type it is closer to valence band, and accordingly you will get this your here your intrinsic material. That means N equals to P, and here your this, obviously this is N type, N greater than P, and this is a P type, P greater than N. So how it is coming in terms of Fermi-Dirac distribution and density of states. So this is, again, this is the difference, or this is the variation of your Fermi level when we'll keep on increasing the doping concentration. So because we have just understood that lower will be the distance between your Fermi level and the conduction band bottom, higher will be the electron concentration. And similarly, lower will be the distance between your Fermi level and the valence band top, higher will be the hole concentration. And similarly, you can see here how this your difference between your Fermi level and the valence band, as well as the Fermi level and the conduction band difference is decreasing with the increase in the doping level. So this is doping level. Doping level, I think you know. This is a number of. So in case of silicon, once again, the number of silicon atom per centimeter cube is of the order of 5 into 10 to the power 2 per centimeter cube. So if you take the 1 centimeter cube of silicon semiconductor, you will get this many atoms. And out of that silicon atoms, now you are trying to replace these atoms. So if we replace, let's say, 10 to the power 14 atoms, that means 14 to 22. So for each 10 to the power 8 number of atoms, you have one dopant atom. And for this case, 17 to 22, that means 10 to the power 5. So if you take 10 to the power 5 number of atoms in this doped semiconductor with 10 to the power 17 order, so that means if we take 10 to the power 5 number of atoms, you will find one dopant atoms when you dope it with the 10 to the power 17 number of N type. That means maybe your arsenic or maybe your aluminum. So this is how this is the changing, like your Fermi level is changing with the doping concentration. And at the same time you can also see this with the temperature. So what is the difference with the temperature? So that is something we will discuss once again, the temperature variation. Now this is the same derivation which we did in last time. So this NP equals to NI square you will get, and from same expression we will also be able to calculate this intrinsic carrier concentration from the band gap. So so just if you consider this equation, and if you take this equation, so you will be able to find out. So from here, another I would say this take home message: see how the intrinsic carrier concentration is depending on the band gap. So your band gap will decide this how many carriers. So because in case of silicon, what is the intrinsic carrier concentration at room temperature? That means at 300 K, it is of the order of I think 1.45 into 10 to the power 10 per centimeter cube. At I think it is mentioned here. No, okay, it is mentioned here. So this is the carrier concentration for silicon at your room temperature. Okay, so now from here you can understand, like if we once again try to recall that band gap. So because for silicon it is 1.1 electron volt, but for other material it may change from like 1.43 for gallium arsenide, like compound semiconductor, or 3.43 for your gallium nitride, like compound semiconductor. So in gallium nitride, what will happen? So your band gap from 1.1 for silicon to it is 3.43 for gallium nitride. That means the intrinsic carrier concentration will be very, very low for this wider band gap material, right? So this is another important take home message. So again, this is the variation of carrier concentration or intrinsic carrier concentration with the temperature, and this is something we have already discussed, if we remember. So we have discussed something like this. If we quickly remember, this kind of graph we have already drawn or we have discussed. So this is the same graph, but you can note here it is 1 upon like 1000 upon t, or that is why the behavior is opposite. So this is again showing how in case of intrinsic semiconductor as well as in case of extrinsic semiconductor, that means in case of dope semiconductor, how the carriers concentration is changing with the temperature. So this is the same thing. Okay. So find that current density or current I, and which is eventually the function of two material parameter, two intrinsic material parameter. One is your carrier concentration and another one is either mobility or velocity of carriers. So this particular guy we already we understood, like how to calculate the carriers. Now in order to quantify this total current, we need to understood this next parameter, either mobility or the velocity. So this concept. So regarding this, we also started some discussion previously. So here we started to discuss what will be the velocity of carriers without any electric field. So this is the energy, the kinetic energy of your electrons or the carriers, and this is coming from the equipartition theorem. And depending on each degree of freedom, we will have the 3 kT by 2 total energy. So this is at certain temperature, at certain. So we only have. So we only have this some temperature here. Nothing else. We have not yet applied any electric field. So from here we understood in the last class, at a certain temperature, the carriers or the electrons or the holes, they are moving very fast within the within the material or within the semiconductor. But remember, this speed or this velocity will not lead to any current. That is why this is also called random thermal motion, because this is entirely random, so it will not give us any current, because for the current, as we know, that we need directed motion of carriers. Otherwise, see, some carriers are just jumping around here and there, and it will not give us any current, although there is a movement. So this is called random thermal motion. And this random thermal motion, as we calculated last time, it is having very significant value. So 10 to the power 5 meter per second velocity is not that low, it's very fast, but it is not giving us any current. So finally, in this current equation, it is not having as such any role. Okay, so the thing is, this random thermal motion, although it is having significant value, but it is not giving us current. And another thing is this, that why this electrons or these carriers have such high velocity. The reason is this guy, so this effective mass, because the mass of electron is very small. So that is why this energy, that thermal energy it has, it is mostly coming in terms of velocity, because the mass is very small, 10 to the power minus 31 kg for your free electron mass. And once again, it will be further lower when we calculate this effective mass. So this is the free electron mass, and this is the effective mass. So since overall this effective mass is very small, so the speed of this carriers will be very high, or this velocity of this carriers very high. Now after this, our objective is to understand what if we apply the electric field, because we know if we just take any semiconductor bar at certain temperature, so the carriers are moving very fast within that semiconductor due to the random thermal motion, but it is not having any net current or net flow of directed carriers, like there is no directed motion of carriers, or we are not getting any current. Now let us apply your electric field. So this is the path. Let's say that continuous, this path is the your electron path, that random path, and here your electron is generated, and here again, once again, it recombined. So because this generation and recombination will continue within the semiconductor if we are keeping it at certain temperature. So now if we apply certain electric field, so what will happen? This random path will take some directed component. Now this dotted line shows this the path of your this carrier or electron after applying your electric field. So then what is that velocity? So that v is the del v. So why this del v? From here it was 0, that directed component. Remember, there is a random component, but there is now coming directed component. Why? Because we are applying this electric field. Okay, so there is a two concept. Don't get confused. So one is the random this push part in the for the carriers in motion, and another one is the directed component, because now we are applying electric field and we get current. Now see that directed component, if we want to calculate that directed velocity or the directed component of this motion or carrier's motion. So if we want to calculate, so this F, that means the force we are applying, it is the electric field, so it is a Q times E, and which is essentially, this is a Newton's second law, del P by del T, and again here we have effective mass, this is the velocity variation, then they are divided by tau c, and tau c is the your this is called mean free time, like This is the time between two collision, or again, this is the average time, of course, because this time may change. So this is here we have two collisions. So this electron generated here, so then it is getting scattered by some reason that we'll discuss soon. So by some reason it will get scattered, and it will change its direction from here. Again, from this point it will change its direction to here, let's say. So this way it will change. Now the time it takes, or the time between two collisions for any particular carrier, is the tau c. So this is, again, this path is called mean free path, and this is the mean free time, tau c. So then if we further simplify this equation, we will find out that LV equals to Q times E multiplied by tau c by m star, and then you will have this Vd, or the drift velocity. So this is the drift velocity, or the directed component, or the component which will give us the current. And this is the velocity. This is coming due to the thermal, or the kinetic energy, or the thermal energy, which we can also write as VTH. This is the thermal velocity. This is a completely random, and this is the drift velocity, which is coming due to the directed motion of your carriers after apply electric field. So here we have both, you have your electric field as well as this thermal energy. So this is here you are having now current. So again, this constant is nothing but the called mobility. So V equals to mu E. Vd, or the drift velocity, equals to mu times E. So from here you can understand that mobility, because okay, so regarding this, you know that there are few high-speed meter devices. Again, I think I mentioned that for this upcoming generation of mobile, we need high-speed device, so that silicon will not work for your 5G, 6G. So in that case, mainly the parameter you should look at this mobility. So this for particular semiconducting material whose mobility is high, so that is suitable for higher generation mobile communication. And if I remember correctly, the mostly the smartphone, that's 4G smartphone we are using now, or the 5G which is coming, there the final this transistor where your signal is going to the base station, and the signal is coming from the base station, in that is called typically RF front end. So in that particular RF section of your mobile, you will find transistor made of a material which has higher mobility. And finally, see, this mobility is related with this effective mass. And again, just to correlate this concept, again, this effective mass depends on your that band structure. Remember that band structure. So narrower will be this, then this your effective mass will be lower. So then now you can see how these are all correlated. Like a particular application, if we want to meet, so then all the way from this material, band structure, everything we need to understand. Okay, now coming back to our this topic, now we have this current. Now the next question is, we have already calculated that our this velocity is very high, thermal velocity. And now this drift velocity, what about this drift velocity? What do you think? Is this very high, this speed or this velocity, as like thermal velocity, or it is very small? So I think this was the like the discussion we stopped last time. So second. Just wait for a second. Okay, just hold for a second. I'll be back soon. Okay, so sorry for the interruption. So now, if we try to calculate or quantify this VD like your VTH, so what is this? So because essentially this velocity of carriers is giving us the current. So now just quickly, if we calculate, let's say, okay, here, just simply your current I equals to nothing but the Q divided by T. Q is the total charge flowing, and per unit time is your current ampere. Now your this Q you can write in number of carriers Q, then we can write this is because this is the current definition, and from the definition of this drift velocity we can write this is Vd into E. And again this is for current density. Now we need to multiply area. Okay, so this is the area of the this cross-sectional area of your device. This is the electric field or the voltage field per unit length we are applying across our device. This is the velocity, that drift velocity. This is the electronic charge, and this is the number of carriers. Now if we try to understand, let's say for a semiconductor which is doped with the 10 to the power 18 number of dopants. So let's say 10 to the power 18 is the number of electrons we have in the semiconductor available, and now this electronic, okay, let me write here. So 10 to the power 18 multiplied by electronic charge is 1.608 into 10 to the power minus 19, and then keep this Vd. So now if we just write E, you can take one, or these are one, you can take like 1 unit area, you can consider like 1 centimeter square or something. So now you can see for 1 ampere of current. So now if we consider 1 ampere here, so the 1 ampere of current you will get. So see this 10 to the power 18 number of carriers you have, and which has a electronic charge of 10 to the power 19. So it will be 10 to the power minus 1 or 0.1. So then now you can easily calculate this Vd for a unit electric field and a unit cross-sectional area. So from here you can easily guess the value, this drift velocity, this value is very small. This is very small here. It is it will be 10 so 1 or 10. So it will be 10 if we consider this all 1 ampere, 1 unit electric field and the area. So compared to this your thermal velocity, now look at the drift velocity. So that means conceptually, the electrons are having very high random motion. But overall, when we apply the electric field, it will gradually move. It will slowly move. This, the entire cloud will shift slowly. This is not very fast. Why? Why it is not moving very fast, and why it does not require to move very fast to give us, let's say, significant amount of current. 1 ampere of current is a very large current. Again, if we consider microelectronics. So then, what is the reason? The reason is here. This guy. Okay, so this guy, this number of carriers. Although the electrons or the per electron or like electronic charge is very small, but we have large number of carriers. So large number of carriers, if it can move very slowly, it will give us significant amount of current. So now let us summarize these two concepts: thermal velocity and this drift velocity. So this thermal velocity is very high. The reason is that small effective mass. Take this different. The reason is very small effective mass. That is why this velocity is very high, which is coming. This energy is coming purely from the thermal energy. And now, whenever we apply this electric field across our semiconductor bar, this is very small. This brief velocity, and the reason is we have lot of carriers. That means total what the charge is very high. So that means, and that is why that high amount of charge does not require to flow very fast to give us some current. So these are the two very important this discussion and this concept. Okay. So now, okay, so following this, just quickly, because our main objective was to find out this uh, conductivity. So now, if we quickly consider a semiconductor, this three-dimensional semiconductor bar. So this is a semiconductor bar, and the current is flowing because we have applied some electric field. And if we take a small cross section within this three-dimensional semiconductor, and now you know that your after applying electric field E, your, let's say this is N-type semiconductor. So then your carriers are moving in this way. And if we just consider time dt, the within time dt, what is the distance these carriers are traveling? This is simply drift velocity multiplied by the time dt. So this is the uh, distance it is traveling. So now, if we quickly calculate this charge dq within that this volume, small section of your three-dimensional semiconductor, this is your nq, sorry, vt dt and area. Q area pt, or This is, I think you already know, but electric field, BD, you can also write as electric field. Just before this, we have derived. So this is a multiplied area. So now if we consider this JP or J, so this is again, okay, first let me write JN equals to NQ mu in electric field. And in case of semiconductor, to find out the conductivity, we need to understand this both the carrier behavior. That means we need to count the total number of carriers, both electron carriers and hole carriers, and we also need to count that their mobility or the velocity. So then here it is, you can say P Q mu P. So the total current density is P mu P plus N mu N Q electric field. So if we once again recall, this is the conductivity. So this up to this. This is the conductivity of your semiconductor. And now see, your conductivity is decided by the number of carriers, holes as well as electron, and their mobility here. Okay, so these two parameters will finally decide that conductivity. Again, this discussion we started with that classification of material considering different conductivity, and we know that insulator has very high resistivity and insulator like very high resistivity, and then your semiconductor has resistivity or conductivity in the middle between your metal and the semiconductor, metal and your insulator. So these are the parameters which will decide your that range of your this semiconductor conductivity or resistivity. So if we remember semiconductor here let's say you have metal and here insulator. So these are the micro, once again these are whatever the calculation we did up to now. So these are all microscopic phenomena we have discussed, and we finally arrived to this particular equation, and how the different microscopic phenomena is leading to this overall like this observation of your material characteristics in terms of conductivity. So that we need to understand, or I hope we understood from this concept. So I will not move further today, or I will not go. So then I'll stop here, and please let me know if you have any question from today's discussion. I'm stopping today. Thank you.